Hi, Will.
Hi, Fee.
Now, can you talk me through some of the stuff about p-values?
Sure. P-values are really misunderstood, actually. Um, so they were invented by Ronald Fisher in the early part of the 20th century um, uh, to help with a process of hypothesis testing. And they're usually described in terms of hypothesis testing, but we don't need to do that. So I'm going to take a somewhat different approach and explain it in a broad conceptual way rather than a mathematical way.
I'm relieved to hear that, Will, because I'm a health professional and I'm really doing my best to try to be evidence-based and look at some of the research articles, and they almost always report p-values. I'm not entirely clear about what it means, so I'm really hoping you can help with that.
Great. So basically, the reason for inventing p-values or using p-values is because of the problem of sampling error. So you're probably going to ask me, what the hell do I mean by sampling error? And a little kind of experiment might help a bit. So if I tossed a coin 3 times as an experiment to find out what happens when a coin is tossed, I might get 2 heads and a tail. And I'd conclude from that experiment that whenever I tossed a coin, 67% of the time, I'd get a head. But if I did that coin toss 1,000,000 times, then I'd get a very sore hand, but I would get a much closer observation, a much more accurate probability of getting heads of just half the time, assuming that it's a decent coin. And so those 3 coin tosses represent a sample out of all of the possible coin tosses that one could do. And 1,000,000 is kind of a large number, but technically I suppose it could be infinite. So when we do a clinical study, we're usually interested in a population, but we only sample part of that population, and we try to draw some inference from the results that we get from making observations within that sample to the whole population. So p-values. So that's the problem of sampling error, is that we're trying to extrapolate from a limited number of observations to the actual reality.
Check I've got this right. So a key reason why we need p-values is because we need something to clarify how good our guess is from about how well an intervention works, based on the little sample that we've got in my study, these guys here, versus what's really true about how well an intervention works for the whole population of people that might have this health condition.
Yeah, so you could do an experiment or a clinical trial with 10 people, and your intervention, you've randomized 5 of them to your magic sparkly treatment and half of them to standard of care. And it happens that in your particular experiment, all of your 5 people had a great outcome. Now, the question is, could that have happened by chance just because of random sampling error? In the same way that if you could toss 10 coins in a row, you might actually end up with heads every time just by random chance. So p-values are trying to express the probability of the kind of observation that you make in your little sample being a true reflection of what actually is happening in the whole population.
So whether the results that I found in my study with my little sample were actually accurate for the overall population of people.
Yeah. So you could imagine that the more people that you have in your sample, if you had a big sample, that you would end up with a more accurate estimate of whatever it is you're trying to establish. Or
How well my intervention works.
So that's one thing. Yeah. So I mean, there are all sorts of observations and things that you're interested in a study, but certainly an intervention study is you're trying to work out whether a treatment works or not. But you could be interested in other things like how well does this particular phenomenon correlate with another particular phenomenon.
So to be honest, I've always thought that the p-value had something to do with how useful the intervention was or how effective it was. But I'm beginning to wonder if I'm right about that.
Yeah, well, there is a relationship between the effectiveness of the intervention. So if there's a very strong effect, then it's easier to detect, even with small samples. So p-values tend to get smaller with larger samples, like I've shown in this diagram, but also with bigger contrasts between the groups that you're comparing. So it's not a very good indicator of the effect size. And it doesn't tell you anything about whether the effect is meaningful at all to the population of interest. So if you did a massive study, you could find a very small p-value detecting a difference of maybe half a point on a pain scale of 1 to 100. But half a point difference on such a big pain scale, you'd say, well, what does it matter? It's just not clinically meaningful at all.
So if I was going to be a really crafty researcher and I wanted to make sure that my p-values always look good, I'd make sure that I measured these infinitesimal, tiny little changes on somebody's pain or flinches in finger movement. They don't actually make any difference to the way that they live their lives.
Yeah, I mean, that's the other thing. The more measurements, the more kind of experiments, if you like, you do, and the more statistical tests that you do, the more likely you are to find a low p-value just by chance.
So what does a good p-value look like then if I'm wanting to know the results from this study, worth paying attention to?
So normally p-values are expressed as a proportion or percentage. So you get a number like 0.05, say. That's the typical way that a p-value could be expressed, and it can vary because it's basically expressing a probability. It can range from 0 to 1. Now, what that actually means is a 0.05 probability of a result if you did the study over and over again in this population. Let me just find my drawing thing again. So if you did this little study over and over and over and over and over again. So in the long run, you just repeated that study. 5% of the time, you would get a result that's quite different and smaller than the result that you observed in your original study. So it's telling you that 95% of the time, you get a result that's the same or bigger, which means that you can be more confident that what you observed in your sample was true. Now, whether 5% is adequate or not is a really interesting question. And 5% tends to be the conventional sort of cutoff for statistical significance, there's not really any clear rationale for that. It's just actually just a convention. And you can imagine that a p-value of 0.00001 would give you much more confidence that what you've seen in your sample is true, and a p-value of 0.5 would give you less confidence. But where to draw the line is dependent on the context. So it's often, one of the things is how radical your observation is. If you find something that is quite unusual and unexpected and goes against a current theoretical basis of practice, for example, then you might want to have a very, very small p-value in order to be very confident about the findings.
And so sometimes some of those large population-wide interventions like vaccines, for example, go with quite a small p-value because the intervention is literally affecting millions of people. So
yeah, so the consequences of the inference has to be taken into account. Yes, that's right.
Yeah, yeah, yeah. Well, thanks, Will. I'd like to pick this up with you again another time, but this is enough to keep me going for now.
Cool. So I think what really follows from this kind of thing is a conversation about confidence intervals, because it's they're a kind of direct corollary, really, of p-values. So maybe we could talk about that next time.
Great. Look forward to it. See you next time then.
Thanks. Bye.